Okay, we have a problem here where we know something about all males 35 to 44 years of age. We know that their systolic blood pressure is 128, so this is our mu, and standard deviation 15 is sigma. So this is general males within that age group. What this problem is asking is we have a sample of executives. They're also males 35 to 44 years old, but instead of just the general population, they're specifically executives in corporations and trying to figure out if they would have a different type of blood pressure, maybe higher, maybe lower than the general population. So they've gotten records from 72 executives. Let's go ahead and assume that this is a simple random sample. And the mean blood pressure among these executives in our sample is 126.07. So you can see right there that the sample mean is lower than the population mean. But we can't immediately, from this information, say that executives in general, not just these 72, but executives in general in this age group have lower blood pressures, because it may just be that our sample just happened to be have fairly low blood pressure. So that's what we're doing the test to find out. We're trying to figure out, in general, do male executives in this age group have lower blood pressure than the overall population of males in that age group. So the first thing we want to do is set up a null hypothesis. A null hypothesis would mean nothing is going on. There's no difference. In other words, there's no difference between executives and the general population when it comes to blood pressure. So what we say is, if there is no difference, this is the null hypothesis, if there is no difference, then the mean of the executives will also be 128, right? We already know that the mean of the general population of males 35 to 44 is 128. And if there's no difference between them and executives, well, then the executive mean should also be 128. Our alternative hypothesis, if this turns out not to be true, would be that the average of these executives, or of executives in general, males 35 to 44 years old, is not 128. So either it is the same or it's not. And for these simple conditions here that mention, it goes into this a little bit here, we're just looking, can we reasonably assume it's a normal distribution? And can we assume that the sigma of the executives is also 15? So let's go ahead and assume this. Pretty soon, these are unrealistic things. Pretty soon we're going to get into some much more realistic scenarios in later chapters. So what we're looking for now is what's called the Z-Test Statistic. We know that we have this particular sample mean right here, and we're assuming that we have this population mean. We always assume the null hypothesis. This is why they're called null hypothesis tests. So assuming that, we're going to use the calculations that we used back when we were looking at the central limit theorem. So our Z statistic is our particular sample mean minus population mean of the null hypothesis. We have the 15 from our sigma, and our sample size was 72. So working through all that, you get a Z-test statistic of negative 1.09. And now what we need to do is find the p-value to get a sense for how unusual this kind of Z-test statistic is. So we look at table A to get that negative 1.09. And if you look it up on there, you should get 0.1379. So what's going on here with this 2? Well, if we have, we're trying to figure out this negative 1.09, how unusual that is. But because way back in the beginning, we didn't specify whether we thought the executives had a lower or a higher blood pressure than the average male in that age group. All we asked was it a different mean? Because we could be lower, could be higher, what we need to account for is in both directions. In other words, how unusual would it be to get a negative 1.09 or more, or a positive 1.09 or more? Because we didn't specify direction, this is what's called a two-tailed test. Looking up that negative 1.09 in Table A, you get 0.1379. That gives you the area to the left, then the proportion of Z-Test statistics that would be lower than negative 1.09. And then we have a mirror image here, so we'd also get 0.1379 that would be above positive 1.09. So overall, once we combine those two, once we add them together or multiply by 2, however you want to do it, we get a total p-value of 0.2758. What that tells us is, if the null hypothesis really is true, if there is no difference between executives and the general male population in this 35 to 44 age group, we would expect roughly 27–28% of our samples to give us a test statistic either this extreme or even more extreme in either direction. So whether it's this negative direction less than negative 1.09 or the positive direction above 1.09, this area right here, this total area, is about 27%. So is that good evidence that against the null hypothesis? Is this really unlikely to have a 27% chance? Probably not. That's why it says it's not good evidence. A typical threshold is about 5%. If something is less than 5% true, then we start to doubt that the null hypothesis would be true. In other words, we might have really good evidence against the null hypothesis. But in this case, we didn't get that. We only had 27% at the time, a p-value of 0.27, much higher than that typical threshold of 0.05. We did not get good evidence against the null hypothesis. In other words, we're not able to conclude that executives have a different blood pressure in general than the overall males in that same age group. So we're not able to conclude that they're the same, but we're not able to reject the null. We're not able to get evidence that there is a significant difference.